Scripts, let's get started. Welcome back, everyone. We are going to be talking about the kind of very important topic of distances today. This is kind of the start of the semester where the lectures. The first few lectures were kind of focused on building intuition for what we'll be doing and kind of laying stuff out and getting you prepared. We're going to be much more building up a foundation of what we're going to be doing from here. So I'm going to start with some really basic and important ideas of the concept of a distance and the properties that we want a distance and the modeling choice that goes into choosing a kind of the distance you'll actually use. So I assume people have probably heard of distances and worked with distance before, but so this may be pretty fundamental, but I also expect there'll be some stuff which is new as well. Okay, so also, the first homework assignment is due today. I quietly moved the deadline back till midnight. I don't plan to always do that. I want you to do it and come to course, but I know this is the first assignment and the second week, and so I was a bit more flexible. It's also on Gradescope, and so if you haven't used Gradescope before, there's something where we ask you to mark in the PDF you upload where each question is. If you do this well, this saves the TA who'll be grading it a lot of time because they'll be able to flip right to that question if they're grading it and they have to spend a lot of time figuring out where the answer is. They're going to be in a bad mood and they probably won't grade as well. So again, we'll try to be fair and everything, but for your own sake and for saving everyone's time, it'd be great if you can try and make sure you do that well. Again, it hasn't closed yet because I extended the deadline. So if you felt like you didn't do a good job on that, why don't you go and fix it? All right, yeah.
Are we always going to do our assignments on LaTeX, or are we going to do
again, it does not need to be in LaTeX. I want you to produce a PDF where things are clearly labeled and so it's easy to read and find the assignment. The LaTeX, we have the overleaf template. We have everything set up for you, but if you want to do a different way, that's fine. You can do LaTeX inside of Jupyter Notebooks, but if you have a comment section, you can write in LaTeX and if Markdown can compile the LaTeX. So you can write most stuff in there if that works for you. As long as it's easy for us to find it, you upload a PDF that's marked. Yeah. So is there another question or good? Great. So, okay. So we'll be talking about distances. Okay, so again, I'm going to kind of start from a basic foundational point of view. Again, we're going to have data, which is going to be X, but this data will be in some space, and I'll write this as kind of script X. I won't keep writing this, but our data, remember, is typically going to be a set of things, right? X equals X1, X2 up to Xn. And so these are the observations, the finite examples of things we get. There's some space that they're drawn from. Okay, so normally, and so we'll mostly set that this is going to be RD. This choice will imply that each Xi is going to be equal to Xi1, Xi2, up to Xid, right? So this is some space of things, and we'd like it to be as a vector, right? And we talked about the word vector embeddings to say, hey, I'd hopefully convince you can represent words as these vectors and then think about them that way. But lots of data will be we'll want to have it in this format where it's represented as a vector. Some of these things are more general. And so we'll get to this. We'll talk about examples where the space of things is the space of sets, okay? Or it's going to be a special class of vectors, or it's going to be just strings of text, okay? We might get to example there, okay? But for now, think of there's a space of all vectors. Our data set is in here, and then a distance. Okay, our distance is going to be let me use uppercase D. A distance is going to take inputs from this space. Okay, what does this mean? There's this script X that I'm trying to write here. Okay, and we're going to take two elements from the script X space, and we're going to output a real value greater or equal to 0. Okay, so greater or equal to 0. So and so this will be a kind of what a distance is, right? It's measuring the kind of how close two things are. And so this is small. So we'll say D A B is small if A and B are somehow close to each other, and D A B is going to be large if A and B are far. And this is a way of quantifying this. Okay, so right, so the most common way you probably see this is that you have kind of two coordinates, you have 2 points, you have a point A. For instance, this could be coordinate 3, 5, and you have another point B here. This could be coordinate 6 minus 1. And then the notion of distance between these 2 points, again, this is in when little d is 2, so a two-dimensional point. You often think of the distance between them as the length of the straight line in between. Okay, so this is how you would quantify distance, right? And so if you have not, probably seen this before, this would be called the Euclidean distance. Euclidean distance between A and B is going to be, in this case, A1 minus B1 squared plus A2 minus B2. This is the second coordinate difference squared, the square root of this. So in this example, this would be 3 minus 6 squared plus 5 minus -1 squared. This is 3 squared plus 6 squared, and this would be 45, square root of 45. Okay, so this is just, okay, so just to make it clear, hopefully you've seen all this before. This is an example of a distance. And so we're going to talk about classes of distances where this will be kind of the canonical example. This is one of the two most common distances you will use, but it's not the only option. And sometimes you want to change how you measure the distance, and that will drastically affect the outcome of the data mining. Okay, so often the input to data mining in an unsupervised sort of setting is two things. One is the data, okay, and the second is the definition of the distance. Okay, we aren't necessarily given labels on the data to say this one is a positive and this one's a negative example, or some value associated with it to do supervised learning. We're going to have to try and infer something based on how close points are to each other, how things are structurally similar. To that, I need to be given the distance as an input. We will, in some parts of this class, we'll talk about, okay, how do we choose the distance, or how do we learn a good distance for something? Okay, but for a lot of the algorithms we'll get to, I will tell you, you're given the data and you're given the distance. This is kind of the standard format. And this part is often unspoken. It's often implied to be the Euclidean distance here. Okay, not always though. And it's kind of, I'm not even sure it's now, for a long time, it's been the most common distance. It may not be the most commonly used distance anymore. Okay. Okay, and I'll kind of explain that throughout the lecture, and then we'll see a bit more some of this over the semester as well. Okay, so that's why it seems maybe a little bit pedantic to kind of, okay, this is the distance and how we use it, but it's super important and essential for much of whether when you apply an algorithm and a method to some data that you have, whether the output makes sense or not, often depends on how you choose the distance. Okay, so let's talk about metric. So distances. This is a class of distances that has a very special property. And so these properties are kind of often the basic thing that you would want out of a distance. You have a choice. Well, at least I want it to be a metric. Turns out you don't always, but there are a lot of nice mathematical properties that are true as long as the distance is a metric, and some pretty wild things are kind of metrics that are very abstract. Okay, so who's heard of a metric before, of a type of distance called a metric? Yeah. Okay, so what are the properties of a metric? So you can define it by a few properties.
Is it for like a triangular property?
Yeah, the triangle inequality, yeah. Okay, I'll write down 4 properties. We'll see if we can get them all, and I'll spell them out. The triangle inequality, just to match the notes, this is the 4th one in the notes, so I'm writing it 4th down here, a space above it. This one is kind of the one most associated with the metric. It says that if I do DAB is always less than or equal to DAC plus DCB. Okay, this says that if I've got 3 points here, I want to go from A to B, and I look at this distance here, and I measure how far it is from A to B. And if there's a 3rd point, C, and I consider, well, what if I went to C and then I went from C down to B? Can I get there faster? Okay, and the triangle inequality says no. If the way you're measuring distance is a metric, then it satisfies this triangle inequality, and it's always faster to go from A directly to B. It never is faster to go through this portal or something magical that breaks our a conventional understanding of the physics to go through a wormhole C, somewhere near C, right? You can't do this somehow. And so this triangle, that's why I call it triangle inequality, because you can draw a triangle and kind of with your eyes kind of see this should be true with the straight line Euclidean distance we talked about. Yeah, not all distances will have this property. Okay, so I have another want to offer. Someone else want to offer another property of a metric distance? Yep. Oh, okay. So this is, I'm just mapping the layers in my head. So yes, this would be called the symmetry property. And let me again write down the letters D of A comma B. So the distance between A and B is equal to the distance between B and A. Okay, this makes sense, right? If I do look at the straight line distance between 2 points A and B, well, it's between 2 points A and B. I didn't say from A to B. Okay, when would this not be true in your everyday life? This kind of makes sense on paper on the board, but yeah. Yeah, so if you're walking up the stairs and down the stairs here, I don't like elevators, so I walked up and down the stairs here. Probably faster go faster go down the stairs, right? You can go faster down the stairs, right? So if you're measuring in time it takes you to get from here to the first floor, it's probably faster to go from here to the first floor than from the first floor up here. Right? Another one is if you're driving, right? If you drive and you have a bunch of left-hand turns, you probably have to wait at a light until you get an arrow, and it's faster if you are going the same route but backwards and you have a bunch of right-hand turns, right? So sometimes if you're measuring the travel time between two places, then you don't have this symmetry, but that's kind of the natural way to measure distance between things is how long does it take you to get there, right? On Google Maps or something, you ask for a route. Well, you can, there's a hidden option to optimize the distance traveled, but typically it optimizes the amount of time it takes. And that is not necessarily symmetric. So it's not necessarily a metric either, which will make some things odd. And they do a lot of stuff that kind of, their algorithms have to be very careful to deal with the non-metric property. Yeah. Well, okay, it's a distance in the sense of we want to design an algorithm. So let's say you're given a bunch of spatial data points, a bunch of locations on there, and you want to, well, one thing we'll talk about later is clustering these into groups, right? And I want to kind of make coherent groups of points. So let me give you an example. I have a bunch of restaurants that I'm putting on a map. Okay, and you might think, okay, what's the right way to cluster them? But maybe there's like a river that's a river in between them. And there is some bridge up here, but it's a very slow bridge. Okay, so if I were to cluster these, I may want to look at the time it takes me to get between these points. These points are close in terms of these 2 points. It might be close in terms of distance, but this point in terms of travel time is much closer. These communities are more coherent with each other. And so if I measured, I say I have a bunch of data objects and I'm given a distance that I can calculate. I put it in, I ask Google Maps, what's the time it takes to get between these? I can generate a distance. And then I can use this for my clustering. And the left and right side of the river is going to be more coherent than kind of maybe 4 clusters that, or maybe trying to put these 2 groups together and then other clusters on further away, right? So sometimes the travel time is the relevant thing. And all of Google Maps and transportation stuff is really based on travel time, not necessarily the Euclidean distance. Yeah, so this modeling makes sense in what the output of how you group things are. Yeah. Yeah. Monotonicity of the function. Yeah, okay, great. Yeah, so this would be, I will call it something different. I'll call it positivity. This is, so the monotonicity is a combination of these positivity, which means that DAB is greater or equal to 0. So it's always greater or equal than 0, positivity. Okay, and the triangle inequality. So then as you're going further away, the distance is getting further because if I stopped anywhere in between, it would have to be shorter based on triangle inequality or so monotonic means non-decreasing. As I get further away, the distance is not decreasing, right? And so that's true as long as on any route, the distance is always getting further away if I'm taking the shortest route to something. It's not, there's some properties of a geodesic, which is what you want, which is a class of metrics, but monotonicity, I'm not quite sure how to define it. In all the abstract senses, we can apply this metric definition. Okay, if the monotonicity idea did make sense to you, don't worry. We won't necessarily need it, but if you're asking about it, we don't quite need something that strong. but we need this positivity property that the distance must always be greater or equal than 0. This was kind of in the definition I gave on the previous slide, where I said the output had to be a real value greater or equal than 0. Okay. Okay, there's one more.
I don't know what it's called, but it's the distance from point A to point A should be 0.
Yeah, okay. Okay, this is part of it. Okay, this is going to be the identity. Okay, so I'm going to write this. I'll say A distance between A and B equals 0 if and only if A is equal to B. Okay, this part, okay, means that, okay, so if I don't have this and only if part, then I say the distance between A and A is exactly 0. If I put the two objects in, I measure the distance, and the two are the same object, the distance is always 0. Okay, this is easy to achieve. This and only if means that I can't put two different objects in and have the distance 0. If they are different objects, they're different points in the space X that I care about, the script X I care about, then they cannot have a value 0 if they are not exactly the same. And this can sometimes be a little bit trickier to achieve. Okay, and so you don't always need it though. Okay, so there are some subclasses of metrics where if I don't have this, if I don't have this green part, else I would call this a quasi-metric. Okay, so I have triangle inequality, symmetry, positivity, and A distance from A to A is equal to 0, but I don't necessarily have the other direction. That two different things might end up having a distance of 0 between them. Okay, sometimes this happens where I have two different people and I collect data about them, and they're completely different individuals, but the data I've collected matches exactly. They have the same name, they have the same birthday, so there's a lot of similarities in the database, but they're actually different people. This could happen kind of accidentally sometimes. And so you don't always have this identity property. Okay. So there's also instances where so if I don't have the symmetry, then I would call this a pseudometric. Okay, so sometimes I don't have the symmetry property. Okay, so for instance, if I am measuring stuff by travel time on a map, right, I can actually show I have the triangle inequality. That I can never take shortcuts that make it faster. It could be the same time if the best route is through C, but I'm always going the fastest route everywhere. So I can get the triangle inequality. I get the identity, only 2 points. The travel time is 0 only if they're the exact 2 points, and the travel time is always positive, but it doesn't necessarily hold for symmetry. So this would be called a pseudometric instead. Okay, quasi-metric and pseudometric don't, those are the terms for them. There's not so important you memorize them, but these properties of a metric are kind of very core, nice properties to have. It seems like you would always want some version of these properties if that was possible. If you have two options and one satisfies the metric properties and one doesn't, take the one that satisfies the metric properties if you don't know anything else. And we'll see throughout the semester some properties, some algorithms that say this algorithm will work for any distance that satisfies a metric property. Okay, and so we'll be able to apply things in settings that aren't necessarily the Euclidean setting. Okay, let's go to a class of distances that are that satisfy the metric property called the LP distances. And these are defined generally as follows. The distance, and there'll be an LP distance. I'll put a P beneath. between A and B, and we'll assume that A and B are going to be vectors in RD. Okay, so these are defined for vectors in RD, and we'll say that LP distance between A and B is going to be defined as follows. AI minus BI, these are the ith coordinates of these 2 points. I'll take the absolute value of the difference between them. This is all the way I'm going to interact with the data points is the absolute value of the difference. So that means that's going to be a symmetric operation. I swap A and B, this will be the same. I'm going to take it to the power P. Okay. I'm going to sum over all values 1 to D. So of all the coordinates, so for each coordinate, I'm going to compare the coordinates and measure the absolute value and the difference between these scalar values of coordinates, take it to the pth power, square, sum up all of these things, and then take it to the power 1 over P. Okay. So P will be a value which parameterizes this. And it's nice that I take something to the power P and then something else to the power 1 over P. Kind of a little bit weird to think about this, but it's good in that the units are going to carry over. So if I have something measured in feet, well, then I take it to the power 3, so it's feet cubed, but then I take it to the power 1 over P, so then it's back to feet again. So the final value is in feet is in the original units for any of the values of P here. Okay, because these kind of cancel out the way they change the units. Adding doesn't change units and stuff like that. Okay, and I'll often write this as generally as a norm between the vectors A and B, and this would be the pth norm. Okay, so that's equivalent to this definition. This means I'm doing a vector operation in here between the vectors A and B, and I get a new vector that is the difference of A and B inside of this norm operation, and that just compresses this term to be just that difference vector. So I take every element of the difference vector, take the absolute value, take it to the pth power, sum up the terms, take it to the 1 over pth power. Okay, so we already saw a version of this already. What is the D2AB? Right, this is the most common one here, and this will be AI minus BI. And I don't need the absolute value because if I take it to the power 2, well, this always makes a positive value. Squaring something always makes a positive. I don't need the absolute value. I sum up these terms, I equals 1 to D, and then I'm going to take the square root. The 1 over 2 power is the square root. Okay, so I'll write this as just A minus B2. And this one is universal. So if I just write a norm between A and B, it's implied that it's a 2. Okay, so if I don't write the norm, it's implied it's a 2 between vectors. And this is again the Euclidean distance between A and B. This is the straight line distance we had on the first slide. Okay, so this is the standard way you measure distance between two things with a straight line is the Euclidean distance. It's an example of an LP distance. Okay, I will tell you all LP distances are going to be metrics for certain values of P. Okay, what's another common example here? There are a few ones that come up and are quite common. The L1 distance is also nice. Okay, this one you can simplify the sum over 1 to DI from 1 to D. Now I do need the absolute values here because I'm taking them to the power 1. The power 1 doesn't do anything, and the power 1 over 1 also doesn't do anything. So this is it. I'm done. I don't have to take the powers. All the powers are 1. Okay. This is also is a metric different distance, and you can think of it like it's sometimes called the The Manhattan distance, I like it to call it the Salt Lake City distance, because if you have 2 points downtown and I want to travel on the blocks, it measures the distance if I'm traveling on the blocks. I have to walk on the grid. I'm measuring the distance along one coordinate and adding it to the distance on the other coordinate. It doesn't matter which blocks I take as long as I'm monotonically getting closer. So I don't want to go down here and over and back up. That would be longer, but any choice inside of this rectangle that's always making progress will give me the same distance, right? So it's the same as if I go here, right? That's the distance in the first coordinate and the difference in the second coordinate. I'm just adding those up. Okay, Manhattan has these weird streets that cut through the middle. Downtown Salt Lake City is a better example. Okay, so this is also is a metric, and this one has sometimes is much easier to work with, and we'll actually see some really important properties that happen when you use this kind of this choice of a distance. Okay. There's one more common one that comes up a little bit less often, but is still important. If I write orange, can you see it? Maybe let me do a different color. D infinity. Okay, what is the infinity distance? Okay, this is a little weird here. What's going to happen? Let me write this out first. A minus bi to infinity. Let me write infinity first here, and then you can kind of puzzle at it. And then I'll change it to p. 1 over infinity. Okay. Yeah, so this is kind of weird. This is not well defined. Okay, so I need to fix this. Instead, I need to say p here, and let's take the limit as p goes to infinity. Okay, now it's well defined. Okay, so I'm going to start with the L1, go to the L2, go to L3, L7, up to p is up to a million, right? What's going to happen? What's going to happen here? This form is not useful because I have a limit in the definition. How do I calculate a limit here? Well, so for everything, I'm taking to a 1 over 1 millionth power. Before I did that, I took something to the millionth power. So those kind of cancel out. So yeah, so I want to think about what happens in the limit, and then I'm actually not going to. Okay, so how this is defined is actually is going to be the max of I in this set of numbers D, AI, BI. I'm just going to look at the max. Okay, and I'm going to try and convince you that this in the limit is going to approach the max. Okay, I'm not going to write a calculus or measure theory proof here. Okay, but what's going to happen if I have a value? If I have two distances here, let's look at this example. This first one, the first coordinate had a distance 5, and the second coordinate had a distance 3. So I measure the distance between here, right? So the max is going to be 5, right? That between the first coordinate of A and B has the difference of 5. Second one is 3. So I'm going to say the L infinity is going to be the max of these. So what's going to happen if I do the L2 distance? Well, I'm going to do 5 squared, it's 25, plus 3 squared, it's 9. And I add them together, and then I take these square root again. What if I do to the power 3? The 5 becomes 125, and 3 becomes 27. That difference is bigger. What if I take 5 to 100 and 3 to 100. 5 to 100 becomes much, much, much bigger than 3 to the 100. And it dominates. When I take the 1 over 1/5 power, the part from the 3 to the 100th power is going to be noise. And so only the largest term is going to kind of cancel out here. And there are going to be other terms here, but they're going to have an effect of 0 when I take it to the 1 over p power if its p is large enough. So only the largest distance will actually matter here. Now, it's not quite true because there's some technical issues, because if there are two distances that are exactly the same value, then I'll add them up before I do this. And so if the values are tied, it's not quite the same thing here. So we're, this is not the technical formula. So we're actually going to just define d infinity distance as the max here. Okay, and so if you write, this will be the infinity norm here. And so this also makes sense as a distance. I can define it for any value p, but in the limit it approaches the max unless there are ties in coordinates, these kind of fairly rare cases. Okay. So these are the ones that we mostly care about. Let me show a picture here that I think sees an important way how these fit together. I'm going to draw a picture here where I'm going to have 2 points here, a point A, and then I want to look at the space of all points at distance 1 away from A. But I have a different choice of the distance here, right? So I want to draw, now the goal is to draw all points where the distance, the LP distance between A and B is equal to 1. All points B in R2 here. Okay, so if I draw all the points, so for the, okay, so I'm going to say that this point right here is a distance, is the coordinate, this is, x coordinate is 1, the y coordinate is 0. See if I can match this 8 tick marks. This point, this will be 0, 1, right? This is 1, 0. I can also go negative. This will be 0, -1, and this will be -1, 0. Okay, so these points will be kind of a guide here. And now let me draw the L2 distance. The L2 distance looks like a ball or a circle. Pretty good here. And so this is for p equals 2. The red circle is kind of drawing all points B, which are a distance 1 away from A, right? So this distance, the straight line distance is 1 in each of these things. And I can hold a piece of string and I can kind of pin it here. And these are all the points where the string is a distance 1 away. This kind of makes sense here, hopefully. Okay, so this is good, hopefully makes sense. It goes through these 4 points. What if I do p equals, how about p equals 1? What happens with the L1 distance now? What do you guys think? So tell me one point that's an L1 distance of 1 away. L1, remember, I'm summing up the difference in coordinates. I've drawn some special points. Pick probably one of them. 1, 0. Good. Okay, this point satisfies that the L1 distance right here from A is exactly 1. So this is good. Okay. How about this point? Does this one satisfy too? Okay. And I'm guessing some points in between here also satisfy it. Is it exactly the same points on the circle, or is it something else? How do I think what happens in between? Yeah, so 1 over 2, 1 over 2. I go halfway right here. This should happen, right? This is the point 1/2, 1/2. Okay, what about if the x coordinate was 3/4? What should the y coordinate be? 1/4 should be here, right? How about if it was 7/8? And it should be 1/8. What is this? What's forming here? Well, what do you think the pattern is here? It's going to be a straight line. All right. So all of these points on this straight line are kind of a distance exactly 1 away under the L1 norm. Okay, what's going to happen the rest of the sphere? Yeah, so it's going to be a diamond. Okay, so it's also going to go through these points. It's going to be a diamond here. Higher dimensions in 3 dimensions, what does this look like? Let me just, it's not quite a cube here. It's a little bit weird. In 2D, where there's the rotation with the cube will make sense in a second. But there's the third, if I take this third axis out, it's going to be here too. And then there's going to be a triangle, a full dimensional triangle, which will form the surface here. And another triangle here, another triangle here, another triangle here. And the same in the back. So we'll have 8 sides. A cube will have 6 sides. Higher dimensions is called the cross polytope. Okay. So this is it's a more in 2D, it's a square, again, a rotated square, but in higher dimensions, it's a bit more complicated to think about. We'll come back and use the geometry of this later in the semester. It'll be very cool. But it's very, very pointy. It's got corners along every one of these axes and pointy edges and stuff like that, which will be great. It's also is convex as well. Who knows what it means to be a shape to be convex? Who's not heard about convex shapes? Okay. Yep. So that means that if there are any 2 points inside, I draw this one definition, I draw a straight line between them, it stays inside. This will be true in higher dimensions as well. This is an important property. Okay, let's do the L infinity distance. What's the L infinity distance? Give me 1 point that has L infinity distance 1. 1, 0. Yes, they're all the LP distances are going to go through these 4 points I marked. Okay, what is another point that has L infinity distance of 1, other than these 4 points? 1, 1, yes, up here. So this one is also part of the L infinity ball, or the L infinity sphere, because the boundary of a ball is a sphere, right? So these are one-dimensional spheres that lie in 2 dimensions. Okay. So and how can I fill in between these 3 points? Yes, it's going to be a box again. This will be a rectangle here, or a square, and so the same will be true here as well. And so this will be the L infinity ball. Okay, for P equals infinity. Okay, and this is also is a convex shape. Okay, so we didn't talk about other shapes here. What do you think an L3 sphere would look like? Or an L4 sphere?
Somewhere in between.
Yeah, these are nicely nested, right? The LP sphere will be inside of an L kind of the ball. So kind of an LP ball will be a subset of the LP prime ball if this is subset if P is less than P prime. Okay, it'll be less than equal, in fact. Subset equal. Okay, so it'll be a subset of it, so it'll be inside. So that means if I were to try to draw the L3 ball, it would look like this. It kind of bulges out. Remember the the red one was supposed to be the perfect sphere, as perfect as I could draw. And then this L3 ball, this is for P equals 3. And it's kind of bulging out towards these corners. As P gets bigger, it kind of approaches these corner points here. It's kind of this limiting property. Okay. Okay, how about an L1/2 ball? What about P equals 1/2? And define it, right? So what would that look like? Yeah, it's kind of, yeah. So it's still going to go through these points, but it's going to kind of curve in here. Okay, and this is weird. No one uses an L1/2 ball for anything. Okay, so this would be kind of P equals 1/2 here. What property does this not have, as illustrated by this orange line here? Or not quite illustrated by that line, but I could draw a similar line that would illustrate it. It's not convex. That's right. I could pick 2 points here, and the straight line would go outside the shape. So it's not convex. Okay, so this causes lots of problems, including the triangle inequality gets violated when you lose the convexity here. Okay, there's some argument I won't go through, but if you don't have convex shapes here to define the balls, everything inside of that is within a distance 1 defines a ball, then you don't have triangle inequality. I could in fact define a distance by a metric distance by any symmetric polygon that's convex around, it's to be symmetric around 0, and it's convex, and that defines that can define a metric distance as well. Okay, these, I don't know, I've used them a couple times in some mathematical stuff, but maybe in practice even. Okay, so these are kind of some cool properties. So so we can say that LP distance is a metric for P in including 1 up to infinity plus infinity, because I have the special definition for max. Okay. Again, there's issues exactly defining it at the limit, as you pointed out. But if between 1 and infinity, it is a metric because, and you can argue it because these shapes will be convex, and that will be the property that you need. What you need to remember is kind of this, that the LP distance is a metric for these values of P, right? So this is a general class of metrics. And that means there's a bunch of algorithms that will run throughout the semester and will say, well, you have vectors and you can choose any distance that's a metric and the algorithm will work fine. So which one do you choose? Right? You have a choice here of which distance to choose, and depending on which you choose, your algorithm will give you different answers. So we'll have to, so just knowing it's a metric is not enough to tell you which distance to use. Okay, great. I want to show you one of my favorite pictures. I'll ask you a question in a second. Okay, I like, it's one of my favorite pictures because it illustrates what not to do. This is a picture of an actual sign. I don't know if it still exists. There's a city, so Nukayama. It's in California somewhere in Eastern California, someplace in the desert. You can tell by the old cars behind it. When I was writing my book, I was worried about copyright, and I wanted to include this, and I wasn't sure. I almost drove out there to try and retake a picture, but I wasn't sure the sign was still there. So it's in the middle of nowhere someplace, I think. So no offense if you live out there or if you're from there, but okay. So don't do this. Like what they've done is they've written the population, the feet above sea level, and the year was established, and then they They've added these numbers up here. Okay, does this make, hopefully this makes no sense that you would not ever want to do this, okay? Okay, the reason I tell you not to do this is because there's something that happens in data mining all the time. I'm going to plot some people here. This is person A, this is person B. What do these coordinates mean? Well, this is kind of the height of the person. This is the weight of the person. And now I'm going to say, well, I'm going to use the straight line distance between them to kind of understand how similar are these people. What did I do here? I said, well, the distance between A and B is going to be the sum of the height of person A minus the height of person B. I square it, sounds good. Then I take the weight of person A and the weight of person B. I square it again, but I'm adding these up, right? I'll take the square root at the end, okay? But this operation, this is do not do this, okay? So if I have height and the weight, and I'm adding someone's height or their squared height and their squared weight, even if I use L1 distance, I'm still looking at a height plus a weight. This operation does not make any sense. And this will mean that your resulting distance you've used for some data mining algorithm will not make any sense either, okay? So if you have height and weight and you're trying to measure distance, you cannot just directly do this and assume that the output is going to make any logical sense to it. Yeah, that's a good thing. You should not blindly do this. You can't, there's no one right answer. Okay, for instance, let's say I measure this in height in inches and the weight in pounds. Okay. What if I changed it to be in meters instead of inches? Well, it changes this number. What's worse is that I could have had a third person, let's say person C, okay? So C is maybe, and make it more obvious here. So C is further away from B in terms of the way I've scaled it here. But if I change inches to meters, well, now the meters, well, that's what that's doing is it's really compressing this axis. Now A and B will be, got this backwards, okay? Let's put C up here. This is always be closer. What should I do? C is here, and it's slightly closer to B than A, right? I can draw a circle around B, and C is on it, and A is outside. But if I change it to meters, then this distance becomes compressed, and it doesn't matter anymore. And now A is going to be closer. Yeah, okay, so I've normalized it so they're all between 0 and 1, right? What if I add another person out here? Okay, let's say I normalize it and then I add one more person who is at the boundary to renormalize and rerun everything. It's not a bad idea to do. So if you know what your data set is, you can try and either 0, 1 normalize or fit it to a normal distribution and kind of so the standard deviation is 1. And so this is probably better to do than nothing. But we'll talk about this later in the semester, about what strategies you can use here. Okay, but I started with this word vector embedding example because if you have a learned representation, I learned the distances, so it made sense to compare coordinates. And so a lot of the data you'll get out of a learned representation will be totally fine. They won't run into this issue. Okay. But I want you to be careful about it. If you get raw data and you just compare columns that mean different things, what's the right thing to do here? It's not clear. It's not obvious. This is kind of an active area of the right way to deal. I'll give you some strategies, and you may need some extra information in order to deal with those strategies. Yeah. So what do you hope to do with it? Yeah, so I have an unlabeled data set where I don't know what the coordinates mean, and I want to run clustering on it. Why would you want to run clustering on that sort of data set? I mean, this is a really good question. I don't mean to be kind of antagonistic about it, but like, why would you run in one clustering with those coordinates? I would not try to make sense out of it. It seems like it's junk. If you put garbage in, you're going to get garbage out, right? If you know that they're a learned representation, and you have some, maybe if you don't know where they came from, but you trust it's these word embeddings. I don't know what the 74th coordinate means, but I've been given it with the promise that the distances make sense. Okay, then you can people use these things. You're standing on the shoulders of giants, right? Someone else did it's often kind of a process to do it, and people hand off in between. But if you're just given it and no one tells you which coordinate is more important than the other, or where they came from, or how to treat them, what distance to use, if you're given as your input data and a distance, and I will do this on the homework, I'll give you data and a distance, and I'll say, here are the coordinates. And I say, use Euclidean distance, and I won't tell you what they mean. Okay, that's fine, right? If you trust that the distance makes sense. But if you're collecting the data, or you got data from someone and they said, I don't know where these coordinates came from, then you probably should not put a lot of faith into them, that they are actually meaningful. You can try and run algorithms to try and find like weird stuff that happens and say, try and use that to figure out what the coordinates might mean. That might be interesting, but in general, you shouldn't try and draw conclusions from this. Yeah. Yeah, great. So the question is, if I just give you data and it's vector, and I say that the coordinates kind of are aligned with each other, so I want to, it makes sense to compare coordinates directly and add them up in some way. Which one makes sense here? We'll typically use L2 for a variety of reasons we'll see throughout the semester. Almost everything will have an algorithm that works with the L2 distance. Sometimes it'll work with the metric distance, and occasionally we'll want to use the L1 because it has special properties. In fact, it's the smallest one for which it is a metric, and it's the smallest one for which the shape is convex. That will have certain properties where it's going to be kind of pointier, but still convex. And the convexity will allow us to use things like gradient descent and to solve for things easily. And so the L1 distance will have a few special cases. So typically, if someone just gives you vector data, you say L2. Okay, and the reason is often is algorithmic. Again, there's different trade-offs between how good do you model the problem and how fast is your algorithm. Some algorithms will be faster using L2. And so because they're faster, it doesn't really matter which one you used. I could have used L2.5, but I would have had to run a much slower algorithm. So I'm going to use L2. They're pretty close, so it won't matter too much which one I use. And L2 will be faster because of some special things that cancel in the mathematics. It's also rotationally symmetric, which will have a nice property. Okay, yeah, these are great questions. I want you to keep asking these both through the semester and in your heads the rest of your life, right? If you're doing this, you shouldn't just blindly do these things. You should be asking yourself, what should I be using and why? Yeah. Okay, so we'll have a section later in the semester. We'll talk about a class of techniques called distance metric learning. Yeah, actually, this will feed into one of the other distances I want to talk about called a Mahanobis distance. And this is going to push the L2 distance, make that even crazier. So this will be dm of A and B. And this will be defined. I'm going to write this. It's going to look weird, and then I will simplify it for you for a special case where M will be an element of our D by D. So it's going to be a square matrix. It's a square matrix, and it should be positive definite. Okay, if it's positive definite, then this is going to be a metric. Positive definite matrix means all of its eigenvalues are well defined and they're all real and they're all positive. Okay. We'll talk about how to use this later in the semester, give you more intuition about it. What if I if M equals the identity matrix, which is 1, 1, 1, 1, and zeros off the diagonal, then what is this doing? Then this is equal to A minus B transpose. The identity matrix does not do anything. Okay, so now I have A minus T. These are vector operations. So I'm taking the dot product between A minus B, right? So this is equal to A minus B dot A minus B square root. What is the dot product here? Well, that is I equals 1 to D of A minus B times AI minus BI over all coordinates. What is this? This is just equal to AI minus BI squared. So this becomes the Euclidean distance. So if I put the identity matrix in here, this is the Euclidean distance. If I put a different matrix in here with well-defined eigenvalues, what that's doing is it's kind of stretching the space in some way. And it goes off the diagonal. Each of these terms in this dot product is, you factor it through, is just scaling each of the units. So I'm telling it how to scale the units. And so there are algorithms that we will talk about that will learn the best M for some properties of the data. Now, to learn it, you'll use supervised learning. We're going to need labels on the data. So we're going to need some extra labels to guide us how to choose the distance. And we'll talk about a few variants of how to do this. And we'll particularly be learning these Mahanobis distances. They will act in every way like L2, except we can kind of scale them first. And in fact, you can pre-process this. You can do an eigendecomposition of this and turn it into an affine transformation, which you apply in your data first, and then use this Euclidean. Okay, so we'll see this a bit more later in the semester. But this will give us, learning M will give us a way to choose the distance that is best in this class of distances that best fits the data in some way. This is another class of a metric distance in this family. Okay, so you shouldn't maybe this kind of made sense of what this is doing here, but it's kind of stretching the coordinates. And if it's not identity, it means it can stretch them along directions which are not the coordinate axes. Okay, again, hopefully this will make sense later in the semester, but just know that there is this additional class of distances we can also choose from, which are also metrics. Another big class here. Okay, let me give another important distance here. The cosine distance. Okay, this is probably, if you asked people what distance they're working with and optimizing, and you scale it by how much computational power they use, this distance probably wins nowadays as what people are doing. If you say, I'm optimizing something under the cosine distance, and you scale by how many GPU hours they're using, this is probably the most common one nowadays, which is probably not, maybe not true 10 years ago. Okay. Okay, and so let me define this distance. Okay, this is, again, this works between two A and B, which are going to be in RD, right? So this is our space. The space is, again, RD, and this is going to look different than the LP and Mahanobis sort of distances. Okay, this would be defined as 1 minus the dot product between A and B divided by the norms of A and B. Okay, so when people say they're optimizing the cosine distance, sometimes there's something called the cosine similarity. I'll say they're probably trying to maximize the cosine similarity, which is just defined as A okay, so this, they're often trying to maximize this, which is similar, basically minimizing this, right? Instead of subtracting this value from 1, I just calculating this value. Okay, and so now I want to maximize. So a similarity is kind of like, is an inverse of a distance, and there are two ways to convert between them, and we'll probably one way is to take 1 minus the distance, and you get a similarity, and 1 minus the similarity gives you back the distance. So there's a different way as well, and we'll talk about this conversion a little bit later in a couple of weeks, a bit more. But the similarity is just measuring the dot product between them, between A and B. Okay. Okay. Do you think this is going to be a metric? Is this a metric? Let's kind of go through our rules. Remember, M1 was that it has to be positive. Okay. Can positivity, is this always going to be positive? Yeah, I see some nods. Yeah, so I'm normalizing the distances of the vectors A and B. I'm basically dividing them by their length before I'm taking the dot product, or afterwards. It doesn't matter. It's a linear thing that you can factor out. And so that means that, yeah, I could think of taking, this is equivalent to taking the dot product of the normalized version of A and the normalized version of B. Okay, and these are at most, each length at most 1, and the dot product of two things at length at most 1 is at most 1. So that means I'm subtracting a quantity from 1 that's at most 1, so it has to be positive. Okay, so it has to be positive. What's the largest it can be? So if I can make them so that they're 0. If they're orthogonal, they're going to be 0, right? the dot product will be 0. So 1 minus 0 will be 1. So it can be between 0 and 1, or the dot product can be negative 2. If they're anti-aligned, they're pointing different directions, the dot product will be negative 1. Okay, so it can be between 0 and 2. So this will be in 0 and 2, but it satisfies this positivity property. So it's okay. Okay, how about M2? So this second one, M2, was the identity property, right? So this is that D of A, B equals 0 if and only if A is equal to B. Is that going to be true here? No, right? So how could this not be true? Yeah, great. Okay, so we're starting to understand a bit better what this is doing. I could think of two vectors, A and B. They're both vectors from the origin, but they're sit right on top of each other. And so before I calculate the dot product between them, I normalize both of them to be sitting where A prime is equal to A and B prime is equal to B normalized. Okay, now they both sit on top of each other. And so the distance will be 0 in that case. They'll both have norm 1. And I take the dot product of the vector with itself. They're both of length 1. I'll get back 1. 1 minus 1 is 0. But they came as inputs. A and B were different inputs. Okay, so it doesn't satisfy this identity. But it can if we set the domain equals to S D minus 1. So this is the sphere, the D minus 1 dimensional sphere. This is the L2 sphere in D dimensions. So if I first normalize them as the input, so I say that all the input must lie on S1 here, right? This is the one-dimensional ball. It's one-dimensional because it's a line. A line is one-dimensional even though it lives in 2 dimensions. In general, these are D minus 1-dimensional spaces in D dimensions. And so it's not a big loss of information to remove 1 out of 300 dimensions. I still have 299 dimensions, so this is commonly done. We will often normalize our data if we care about metric sort of properties. And I've lost a little bit of norm information, but now I can argue it satisfies this identity property. Once I do this, then it satisfies the identity property if I assume that all the input has been normalized ahead of time. And sometimes people do it, sometimes they don't. You'll see papers and they often don't say, and then if you ask them, it could be either case. It's been my experience. Okay, so it's not a metric, but we can kind of fix it so far. Okay, M3 was the property, the symmetry property. Okay, this is not like the distance where I was measuring the difference in the coordinates, but does this satisfy the symmetry property? If I swapped A and B, are they going to give me the same answer? Yeah, because the dot product is symmetric. Okay. Okay, so this satisfies symmetry. Okay, we're doing good. Good, we're almost there. Does it satisfy the triangle inequality? Okay, does it satisfy the triangle inequality? Yeah, this is kind of tricky to think about. The answer is no. It does not satisfy the triangle inequality. If people care about this, they often transform it into something called the angular distance. The angular distance between A and B is defined as, okay, get this right, as I undo the cosine part, A minus B. Okay, this is equal to the arc cosine of A minus B. Okay, so this is a trig operation. If I do the angular distance and I assume the domain is actually normalized data, then this becomes a metric. And I'll explain why on the next slide, why this isosceles triangle inequality, what it's doing here. But why would you not want to use the angular distance in practice? Yeah, this is a trig function in our cosine. How does the computer calculate a trig function? It looks it up in a table. Okay, so there are these tables stored inside of Python and Fortran and C, and it looks it up at a table. Yeah, you could do a Taylor series expansion if you want to, but it's not fast. Okay, so if you're thinking, it's many more operations through a GPU or a CPU than just doing a dot product. Okay, and okay, you can change it in this way. This is not really changing the order of things. That if A is closer to B than C, then it will still be closer to C under this distance too. It's a monotone transformation. So it's not structurally changing anything. It's just harder to calculate. Okay. Okay, why is the angular distance kind of a metric? If I think of this S1, this is a space S1, and I have 2 points. Now I'm assuming on here and B, and I'm measuring the angular between A and B. Remember, this is the arc cosine of A dot B. Okay, well, what is that distance actually measuring between these two vectors here? Again, maybe you can think of them as points on the sphere but I think in this case, it's useful to think of them as directions. When I have a point that's been L1 normalized, I've removed the scale information. I only care about the directional information here. What is the angular distance measuring here? Remember from your trig class, what's the arc cosine of a dot product between two things? The what? Yeah, that's right. It's the radial distance of the angle. The angular distance is measuring exactly. This is equal to the angle between kind of A arrow, B arrow in radians, right? So this will be a value between 0 and pi. Right, so 2 pi is all the way around the circle, but I can always go the shorter direction, and that's at most pi. Okay, so it's a value between 0 and pi, and it's measuring the angle. That means it's a geodesic distance. It's always the shortest path on this manifold that is this sphere. I'm always walking the shortest path. That means shortcuts don't help. Okay, you can come up with examples with cosine distance where the shortcuts can help. You can't for the angular distance. Great. Okay. So we didn't quite get to a couple other things, but I have space for them a little bit later. We'll talk about a couple of other distances later, including distances between sets and distances between distributions, probability distributions. So that'll come in a few weeks. Some of them will be pretty simple like this. Some will be more complicated because they're modeling more complicated structure. But okay, hopefully this is interesting. If you have not finished the homework, because it's the first one, I pushed the deadline back with no late penalty until midnight. If you haven't properly encoded the answers in Gradescope, please go and change it. It'll save us a lot of time on the grading things. All right, thanks.